This is a formulary for the many quantities of interest to us in the kinematics of circular motion. I'll be walking through this guided note sheet, so I recommend you have this document handy to work off of. And I'll use some color-coded highlights. Green will indicate quantities relevant to linear or translational motion, so motion over a distance, and yellow will indicate angular or rotational motion quantities, so changes in angle. And we'll start with this circle and this fundamental relationship between the length of an arc around the edge of a circle, so a portion of the circumference, the radius of the circle, and the angle theta subtended by that arc. So our fundamental relationship is this. This sort of defines the radian as a unit. So we say that this angle theta is measured in radians, where the value in radians is equal to this ratio. So it's a dimensionless number, so it's a distance over a distance. This dimensionless ratio of the length of that arc to the radius of the circle. That defines an angle in radians. Okay, so much of what we do from here on out is going to be based off of this fundamental relationship right here. Okay, let's next talk about position vectors. So for an object moving on a circular path, we can define its position vector r. And you see that in pink, I'm going to be highlighting all vector quantities. So our position vector r and our unit vectors I hat and j hat. So vector quantities in pink here. Okay, so in rectangular coordinates, we can define this position by its x and y coordinates. So x I hat plus y j hat. We get the magnitude of that position vector would be the radius of our circle. Or alternatively, instead of these rectangular coordinates, x and y, we can define a position with polar coordinates. So r and theta are the radius of the circle and theta the angle right there. So instead of I hat and j hat unit vectors, we can use a different set of unit vectors that we call r hat and t hat. R hat is a little unit vector pointing out from the center of the circle. Outwards means the radial direction, radially outwards. So out from the center is always positive radial direction. In towards the center is always the negative radial direction. We have other terms for these. Outward from the center is called the centripetal direction, centripetal, and inward towards the center is, oh no, I said that backwards. Okay, outwards from the center is centrifugal. Centrifugal is outwards, and centripetal is inwards. Okay, so these little unit vectors, r hat and t hat, they are unit vectors, meaning their magnitude is 1, unity. But what makes them different from our I hat, j hat vectors here is that these unit vectors rotate as you go around the circle. So if you're located at this position right here, r hat points that way, and t hat, your tangential direction, points tangent to the circle at that point. But when you're over here, the radial direction has changed and the tangential direction has changed. So our r hat and t hat axes sort of rotate with you as you travel around the circle. So they are time dependent if your position is time dependent. Okay, so we'll have use for those. Let's talk about moving around the circle. So if you're staying on a circle, then one thing that will remain constant is r, the radius of that circle. If r was changing, you wouldn't be on a circular path. You'd be on some other shaped path. So here's our fundamental relationship. S equals r theta. And we can take the time derivative of this equation twice to find some other quantities of interest. So starting from here, we take the time derivative once. So ddt of the left-hand side equals ddt of the right-hand side. So ds dt, r is a constant, so equals r times d theta dt. And that gives us this. We define the rate of change of that arc length as your your linear speed v, the rate at which you're moving along the arc. So linear speed v, ds dt, that is the instantaneous rate at which you are moving along the arc. So measured in meters per second, the rate of covering distance along the arc of the circle. Omega here, the Greek letter omega, this sort of curly W, is known as, well, many names, our angular speed, angular velocity, or our rotation rate. And it's defined as d theta dt, the instantaneous rate of change of angle. So it's the instantaneous rate at which this angle here is increasing. If you're moving counterclockwise around that circle, angle is getting bigger over time. So the rate at which that angle is getting bigger, that's what we call our angular speed or our rotation rate, omega. So unit-wise, that's measured in, this is radians over seconds, so radians per second. That's our SI unit, or sometimes we can use degrees per second as our unit. And here's our unit conversion. 1 revolution around the circle equals 2 pi radians equals 360 degrees. Okay, if we take the derivative a second time, so from here do d dt on both sides again, so dv dt equals, once again r is constant, times d omega dt, then we can define 2 more quantities. This, the instantaneous rate of change of your linear speed v, we call our tangential acceleration, a subscript t, your tangential acceleration. That equals r times this quantity, d omega dt, which we define as your angular acceleration, alpha, the Greek letter alpha there. So alpha d omega dt radians per second squared. This is the instantaneous rate at which omega is changing, the rate at which your angular speed is increasing or decreasing. So I want to contrast that with your linear acceleration, your tangential acceleration. I'm going to contrast these 2 quantities here, alpha and at, that are related by this relationship here. So I just described what the angular acceleration means, measured in radians per second squared. Your linear or tangential acceleration, dv, defined as dv dt and equal to r times alpha, that's the rate of change, the instantaneous rate of change of your linear speed v. So alpha is the instantaneous rate of change of the angular speed, and your tangential acceleration, at, is the instantaneous rate of change of your linear speed. So this is sort of a linear quantity measured in meters per second squared, and this is an angular quantity measured in radians per second squared. Okay, let's pause there.